about the introduction. So the previous video talked about gave a basic summary of all the different things we can learn in the microelectronics. And this time we'll talk about a basic introduction. We'll tell you about what the signals are and what the IC, which is the integrated circuit, is. And this is not a topic that is get tested on the exam. It's just it's just a motivation for why you are interested in learning about these topics. So we're not going to do any kind of testing or any exam topic. We're just giving a basic introduction and a conceptual motivation. So let's talk about the introduction. So we're working with microelectronics. So the microelectronics um, So the microelectronics is a field of electronics, and in this field it refers to when we talk about microelectronics, we're talking about integrated circuits. An integrated circuit is called the IC, and IC technology, it puts hundreds and of a million, so hundreds of million different components all on the single chip. So hundreds of millions and maybe billions of components all go on one single piece of the silicon, and that's called the integrated circuit. And when we're working with the integrated circuit, we call this microelectronics. It's a field of electrical engineering. And so we will study in this textbook all the different electrical components that go into these integrated circuit. And the device that these circuit operate on, they deal with signals. So first we need to explain what is the basics. So what is the signals? Okay, so the signals, so signals carry information. So signals, they carry information, but the key thing is the signals carry information over time. So an example would maybe wind speed or the air temperature, whatever. But the key thing is the information, it changed over time. And change over time, we call that time varying ability. So time varying ability. So we give an example. So let's say you have a signal, and maybe this is temperature, and here is, okay, temperature would be in like degrees, and we have the time. So here's time, and time, the units is in seconds. And maybe in the daytime temperature gets warmer, and then around noon is the hottest, and then at nighttime it cools down, and then midnight is the coldest temperature outside, and then goes back to daytime and night. So this is temperature fluctuate over time. And you can imagine that we convert this is a temperature signal. We convert the temperature signal into the electronic signal. So now maybe you have a temperature sensor, and now the voltage is the signal. So this is, how do we convert the temperature? Hypothetically, this example, how do we convert the temperature to the electronic signal? That's called a transducer. And so the transducer, it takes the information from the everyday environment. Maybe it's air temperature, maybe it's wind speed, whatever sensor there is. And the sensor converts it to electronic signal. So that's what the transducer. Think of it like a sensor, maybe like a sensor. And so usually the signals, they usually follow the a shape of a sine wave. So I don't know, maybe a sine wave, maybe V, the signal, we call that A, I don't know, and fluctuates over time, and is equal to the amplitude of the sine wave, so call that maybe VA times sine of omega, the frequency, times t. So the this is the maybe signals, they take the shape of a sine wave. Now omega is the frequency of your sine wave, and omega is in radians per second. So radians per second is 2 times pi times the frequency in hertz is f, and the units of omega is the radians per second, but f the unit is the hertz, so it's the hertz, and hertz is equivalent to 1 divided by seconds. And there's also period, so you do 1 divided period is t, and you do 1 divided by f is time, in the units is second. So the period is how long it takes for the sine wave to repeat itself, and the number of times the sine wave repeat itself in 1 second is called the frequency in hertz. And we can convert frequency in hertz, we can convert that to radians per second, which is the omega. So all signals, they usually take the form something like a sine wave, and there's also a amplitude, so the height of your sine wave is the amplitude, so this is amplitude. Okay. So now the peak value here, okay, the peak value of our signal, this is V, let's call that VA. So that's the peak value, the peak height. And so, earlier in the circuit theory, you'll learn that power is equal to the current times the voltage. But you cannot plug in, let's say you know the current, you cannot plug in here, you cannot do that. You cannot plug in the amplitude there, because that would produce a power, a number that's too high. So there's something called root mean square, and the idea of root mean square is that you take the voltage of the root mean square is equal to your peak value divided by 1 divided by the square root of 2. So it's peak value divided by square root of 2. And the idea of VRMS is if you plug the root mean square, the RMS, if you plug that into the power is equal to current times voltage, then you will get the actual power consumption. So if that's one of the confusions, is that when you look at the sine waves, a lot of people want to plug in the peak value, the amplitude, the peak value, they plug it into voltage times current, and then they get a number for power that's too high. The actual way to calculate power consumption is you take the root mean square, you take the peak value, and you divide it by square root of 2, and then you plug this number in for voltage, and now you will produce a power. The number you calculate will actually be the actual power consumption. So let's say this as an example. So there's a power supply to our home. This is the power grid, is rated at 120 volt RMS. So what is the peak value of the power outlet in the house? Okay, the peak value, recall, is equal to if you rearrange this equation, you get the peak value is equal to the voltage of the RMS voltage times it by the square root of 2. So you do 100 times square root of 2 is 170, 69 or 170, something around there, that much voltage. So A lot of people say the grid is on 120 volts, but the reality is actually the peak value is higher. It's just that we talk about 120 volts because that is the number we use if we calculate what is the power consumption of the sine wave. So very important is us to memorize the value of this square root 2. So square root 2 is 1.414, and there's some more decimal point, but it's very important for us to memorize this value. So there's kind of a discrepancy because in most signal analysis in the signal processing the course, they talk about the signal in terms of the amplitude, the peak value. But if you take power electronics, so power electronics, maybe a third or fourth year of the undergrad, they don't write it in terms of the amplitude, they actually write it in terms of the RMS. So instead they would write it like V of RMS. And where this V RMS is equal to V, the peak, the amplitude, divided by square root of 2. So this is, the left is using amplitude, is called it, we use this in signal courses. And the right side, when we use RMS, we use this in power courses. And it's a little bit confusing because there's not a very consistent notation, but this tends to be the convention people use. Okay, so now let's talk about analog signals and digital signals. So imagine you have a voltage, electronic signal, the voltage, and the voltage, maybe it follows some arbitrary shape, I don't know, like, like this kind of things. The voltage fluctuate over time, so this is called the analog signal. And for an analog signal, there exists a value of VST. There exists a value of V at every possible point in time. There is no point in time when the graph is not continuous. So this is a value exists continuously at every time. But there are some things called the digital signal. And the digital signal, it is only having a value at specific time points. So, okay, and so on and so forth. So at specific time points, we go up and we measure what is the analog signal. And so for the digital signal, and so on and so forth. So for the digital signal, let's draw it out. And we only have some value existing at specific points in time. We don't have value in between. So this is called the digital signal. And the real world is analog. This is the real world is analog, but the computer is this digital signal. And the computer, why is it digital? Because the computer samples the signals at very discrete times. Discrete times is like like T1 and T2 and T3 and T4, at only measuring the value at very specific times. So that's why it's called the computer is said to be digital. Now, at what time instance do you sample? Well, that's called sampling. And so sampling is at specific, the magnitude of the real world signal, we go and measure it at specific time instance, and we call this sampling. And digital signal is no longer continuous, so the value only exists at specific times. So we call this quantized quantized, or we also call it discrete signal, or we call this digitized. These are all the same, refer to the same thing. Now here's the challenge. Because you don't have a value exist at every point in time, how do you go and reproduce the original analog signal? That's very challenging. In some case, it's impossible to convert the digital signal back to the original analog signal, and in that case, you may lose some data. So that is sometimes there is a disadvantage when we use the digital circuit. Now, in this course, the focus is the amplifier. So oftentimes the transducer, which measures the signal information from the everyday world, it measures it in a signal that is very weak voltage. The voltage is very weak. The sensors, the voltage is very weak, usually in the microvolts. So we must do amplification. So there is called a signal processing. Signal processing, there's a lot of things to it, but one thing about it is amplification. And so you want to take the actually let's use triangle. So we take the weak signal and then we amplify it by maybe a big number, I don't know, like let's say it's 10 to the third, and then we output is an amplified version of our input signal. So the output is like a amplifier, a big number times your input. So we call this gain, the value we multiply by. And so maybe the input is very small, but the output is 10 to the third times bigger, much bigger. So that's called amplify. And so how do you write amplify? So amplification gain, we call that gain, is A is equal to the output magnitude strength divided by the input magnitude strength. So it's output divided by input. Okay. So this idea of amplification is linear. So in linear amplification, we just simply form our V out is a bigger version of the V in. So maybe more power. The waveform it initially is very small, but then we amplify it and it's much bigger wiggling. And then but the shape retains the same shape in linear amplification. But unfortunately, that's only the ideal situation. In the reality, many circuits many amplifier circuits will introduce what's called non-linear distortion. And what is that? So nonlinear distortion is when the information it gets altered. So maybe if you try to use a signal of your VI that has a very high frequency, it may not amplify it to your expectation. So this is called we call this distortion because it does not amplify towards our idealized expectation. And we must design amplifiers knowing that this problem exists. We design amplifier so that we have minimized the amount of distortion. And so this is a very advanced topic that we talk about in later chapters and later courses. And one last topic is so one last thing we want to talk about now is called the logarithmic scale. So your gain of your amplifier is just a bigger version of the input. So it's a VI times input times the amplification, maybe it's 10 to the third, 10 to the fifth, I don't know, is equal to output. This is how the amplifier works. But the thing is, this is a huge number sometimes. It could be maybe 10 to the 9. This is not very good. We cannot see what's happening sometimes because, let's say, you would think that, let's say you graph amplification over frequency. You would think that for all frequencies, it amplifies at a value, I don't know, maybe 10 to the 9th or something of your gain of the amplifier. But in reality, due to reasons we will study, amplification works well, and then at a certain frequency, it's maybe there's just a capacitance there, or we don't know. It starts to roll off, and your amplifier does not work past a certain frequency. But sometimes it's kind of hard to see, so it would be nice if we could rescale everything to be in the logarithmic scale. And if you do that, so that's then the graph will be a little bit more clear if you put everything in logarithmic scale, and which we will talk about later. But for now, just know that logarithmic scale, in our we do 20 times the log of the, okay, let's do gain in dB is the 20 times the logarithmic of the a so of the gain original gain, which is V out over V in. This is the logarithmic scale. It's useful when we use in signal processing, and when we graph it on a logarithmic scale, it's much easier to see the graph what happens. This is used in signal processing. If you take a signaling processing course, you will know that the decibel is 20 times log of V out divided by V in. But if you take a power course, like a power engineering course, they will tell you that the decibel scale, so is not 20, is instead is 10 times the logarithmic, it's base 10. Yeah, logarithmic base 10 of output divided by input. So this is used in power engineering.